Following is the foreword for Dr. Penrose's Practical Electrical Signature and Current Signature Analysis of Electrical Machinery and Systems to be released in October 2022. Please enjoy this section, which discusses Dr. Penrose's journey with electrical signature analysis and motor current signature analysis. Contrary to popular belief, the original purpose of motor current signature analysis and electrical signature analysis was not the detection of rotor bar defects in induction motors. In fact, the original purpose of the development of the technology was to evaluate the mechanical components of the electric motor and driven equipment of a motor-operated valve in the nuclear power industry, including lubrication issues, mechanical wear in the gearbox, valve defects, bearing defects, power quality, and the electric motor using the air gap of the motor as the transducer. ESA provides a non-load dependent, repeatable method for evaluation from a remote location, such as the motor control center. The patent and research included work on pump impellers, belted applications, and more, which have only recently been rediscovered as applications for ESA and MCSA. A majority of subsequent papers, academic research, magazine articles, training programs, and other such media focused on the simplest of fault detection methods, the evaluation of an induction rotor, to the detriment of the technology. Over 30 years after the development of the technology for the detection of electrical and mechanical systems, the general reliability engineer, electrical engineer, or technician still believe that ESA and MCSA technologies are primarily used for rotor bar fault detection. Such is the power of media and marketing over engineering and science. This book provides information on the practical application of both MCSA and ESA based upon the experience and research of the author. It is not an exercise in the use of MATLAB or other simulation methods, straight theory, or academic practice, but based on over 25 years of field findings and uses of the technology and a discussion of its future applications. We will focus on ESA, including both voltage and current data collection and analysis, and data that had been collected via the Framatome ANP Empath and the All-Test Pro, LLC outpulse systems, although the information can be applied to any commercial MCSA or ESA device. The book will first split the applications into Section 1, Power Quality, an overview of the application of ESA in evaluating power harmonics, power factor, voltage and current conditions, circuit impedance, and other conditions. Section 2, The Electric Machine, detailed analysis of the electrical and mechanical conditions of AC and DC electric motors, generators, machine tool equipment, and transformers, including wind and solar applications. Section 3, Driven equipment, couplings, belts, pumps, gearboxes, and other driven equipment. Section 4, Tying it together in a wind turbine. Section 5, Machine learning. My first application surrounding the application of ESA was in 1994 in troubleshooting an electric motor at a petrochemical facility in northern Illinois on a Sunday. I had experience from the U.S. Navy in the mid-1980s and had just completed additional training in vibration analysis. The customer had a problem with loading a 4,160-volt compressor motor as it would trip on overcurrent. I was utilizing an IRD fast-track data collector and had obtained information on the stator slots and rotor bars for the machine. With the relatively low resolution of the screen, I noted a 3,600 CPM and 7,200 CPM peak in velocity, as well as others that were inconclusive, so looked at the higher spectra in acceleration. There were definitely peaks in the area I was interested in, and I was about to conclude rotor bars when the customer supervisor said that someone else had been there with a current analyzer and said the rotor was good. I went to my service vehicle and grabbed an inexpensive analog current clamp that I had available and used a trick I was shown when I served on the Theodore Roosevelt, CVN 71, and clamped it around a current transformer cable. The needle made a ticking motion of over 10% of the total current. I informed the supervisor that the motor had a bad rotor, that it was significant, and needed to be repaired, and I was willing to stake my reputation on it. The motor was pulled, brought to the repair shop, where I was the field service supervisor, and inspected. Nearly half of the 3,600 RPM electric motor's rotor bars were fractured. To say the least, I fell immediately into the disbelief category in relation to this relatively new technology. It seemed to make sense, but repeated failings related to findings by several technologies, and some statements related to electric motor theory by the instrument manufacturers, had me balk at suggesting MCSA as a valid field service technology. This was again reinforced the following year at a construction equipment manufacturer in central Illinois, where another compressor motor that we had repaired was having problems. For several months, travel to and from the site each week would not resolve the problem. Vibration data showed a high-frequency issue associated with the compressor, while the on-site technician was using a special application in his vibration analyzer and another technician was using a commercial MCSA device. Both were stating that there were rotor bar problems, and the repair sales department and repair managers had the motor out several times to demonstrate through a variety of means that the rotor was in good condition. The motor base was stiffened based on some observed conditions, and the motor was even sent to a manufacturer to load test for a cost of about $10,000. Our vibration phase analysis kept pointing to the base of the compressor itself from the first day on site, as did a subcontracted third party. During this time, I began performing a little research into ESA/MCSA and noted the relationship between vibration analysis and current signatures. I convinced the sales manager and shop manager to set up a meeting with the customer's management and technicians with the requirement that we could take a look at the data that they were using to make conclusions. As it turned out, they were using a different number for the number of rotor bars than we provided because their data on the motor showed a different set of peaks and there was no pole pass frequency in the motor, so they concluded that the fault was dynamic eccentricity, probably caused by smeared laminations. I was able to obtain a copy of the compressor drawings and discovered that the number that they used actually related to the gear mesh frequency of the fourth stage of the compressor. One of the managers noted that following the repair of the compressor, and while waiting for the motor to complete its overhaul, the compressor repair company had dropped the compressor during installation and cracked the foot on the side of the fourth stage. It had been welded and cleaned up so that no one was aware of this condition. Over the next few years, we had repeated situations where disagreements between the repair company and customers were occurring due to misdiagnosis using MCSA technologies. Each time I would have to perform research into what was being detected and how it was being detected, and started to notice how and what the technology was doing. The challenge was that the resolution was not very good, and it would require at least 50 to 75% loading of the motor in order to separate peaks from power harmonics. In the mid-1990s, the focus in the electric machinery industry was the Energy Policy Act of 1992 and a variety of successful motor challenge, pump challenge, steam challenge, and similar joint industry and U.S. Department of Energy partnerships that were teaching companies that they could reduce their energy costs through right-sizing their motors while moving to energy-efficient motors. As this was being adopted, older U-frame and T-frame electric motors tended to be underloaded in the range of 40 to 60% in many applications. This meant that some of the issues that we were running into with our customers and the use of MCSA was based on misdiagnosis from underloaded data collection and analysis. Once identified, we were able to resolve issues relatively quickly through an explanation between the differences of vibration analysis and the existing application of ESA and MCSA. In 1996, as I was negotiating my transition to the University of Illinois at Chicago's Mechanical Engineering Department as an adjunct professor of industrial engineering and senior research engineer within UIC's Energy Resources Center, I became the vice chair of the Chicago section of the Institute of Electrical and Electronics Engineers, IEEE, and the Fox Valley subsection vice chair. One of the other leadership of the Chicago section was a principal of an engineering firm that oversaw the Chicago pumping stations, which moved fresh water from Lake Michigan through Chicago and the suburbs. He contacted me one day as they had a problem with a vertical 900 horsepower pump synchronous pump motor that had snapped a 24-inch diameter coupling. He brought me several printouts to the next section meeting a few days later, and one of the datasets was MCSA data. I noted a specific pattern around line frequency that looked like pole pass frequencies, a high one-time running speed sideband, and very high harmonics around line frequency peaks that could also be associated with dynamic eccentricity. They did see a one-time RPM frequency in vibration analysis, but had not looked at the number of fields times RPM of the motor, nor the number of amortisseur winding bars times running speed. I suggested that they had bad rotor field coils and was informed that the motor had just gone through a repair process and nothing was found. I looked at my colleague and said, "Yes, but the test instruments say otherwise." I asked for the pull drop tests and we both discovered that this critical test was not performed, so the motor was removed and sent into the repair shop for evaluation, at which point it was found that 5 of the 12 rotor field poles were shorted, and appeared to have been for some time. A review of the coupling brake showed where the fracture had slowly worked its way through the material, starting at a small defect and eventually failed due to torsional vibration. When the engineering company colleague asked how the failure happened, I said that under load the motor would slip and the amortisseur winding would force it back towards synchronous speed, kind of like rotating the shaft with a sledgehammer. In 1997, I became chair of the Chicago section IEEE and had fully joined UIC teaching and performing energy-related studies and research. One of the projects for a West Coast utility was the development of a method that was based on my dissertation and area of research into industrial energy and reliability, the upgrading to energy-efficient motors based upon the condition of the existing motors. The objective was to develop a software tool and data collection method to evaluate the condition of the machines that could be easily applied with several days of training. At this time, I was introduced to the marketing manager for Areva, now Framatome, and their impasse system. It was able to detect most of the conditions that we were looking for, but the project team felt that the technology exceeded the training requirements and it was nearing the end of the project. Between ESA and low-voltage motor circuit analysis techniques, I pursued research into both, which led me to All Test Pro, LLC, a division of BJM Corp at the time, in 1999, where the owner encouraged my pursuit of data interpretation research and development. We only had a set of offline motor testing MCA instruments, which was the primary focus, while we pursued some way of introducing ESA technology to the product line. A conversation with Areva resulted in a contract to brand a special power analyzer that used the impasse software as part of the analysis. By 2003, I was already applying the ATPOL system to wind turbines to look at the condition of the generator and powertrain with some success. However, the sample rate and resolution had much to be desired. Between 1999 and 2004, I worked closely with the UAWGM and the Quality Network Planned Maintenance (QMPM) group in their potential adoption of MCA and ESA for all 74 facilities in North America. In 2003, I also started working with the U.S. Coast Guard on the adoption of the system for the evaluation of Coast Guard vessels, which was also adopted by 2004. At the end of 2004, both the UAWGM and U.S. Coast Guard contractors convinced me to go into business as a consultant to focus on electrical reliability opportunities. In 2005, I also contracted with All Test Pro as a technical consultant and distributor, and by 2008 had completed the research and development behind methodologies for the evaluation of transformers using ESA and wind turbine generators. I had long-term contracts with General Motors, U.S. Steel, and others for reliability programs and ESA training, and a contract with General Motors as part of the hybrid Tahoe development team for insulation systems and electric machine reliability. In 2008, I proposed the inclusion of ESA in hybrid vehicle variable frequency drives based on our research, in which we discovered we could review the entire powertrain, up to and including tire condition, through the hybrid electric motors. Unfortunately, this was rejected due to memory constraints, but the research was published in 2009 and resulted in work related to aftermarket testing and analysis of the GM hybrid products. The published study cut the notice of researchers at John Deere who were working on hybrid construction tractors. Following the economic collapse in 2009, I returned to the repair company I had worked for in the 1990s as their vice president of engineering. We pursued both the work with the wind industry involving root cause analysis and performing ESA, the development of the John Deere 644, and continued research into the field service and reliability of both the GM hybrid Tahoe line and Volt. In each case, the combined use of MCA and ESA was utilized, including adventures chasing a prototype hybrid 644 tractor across a field in a hybrid Tahoe gathering data via a Bluetooth connector between a laptop and an ATPOL mounted on the tractor. The vehicle load of engineers would bunk their heads on the roof as we tore across the open field at about 30 miles per hour, staying within 50 feet of the tractor. The data produced allowed us to make reliability decisions on the final designs and led to improvements as we were brought into the development of the John Deere 944. As part of the early work with wind turbines, we were tasked in the development of a method for the detection of loose or missing magnetic wedges with ESA by one of the international owners of turbines. This involved the detection and then confirmation of the condition using the outpall system, which, based upon the resolution, required some level of loading of the turbine. I did not realize, at the time, but I had fallen into the same trap as most analysts, looking at one part of the data to make conclusions. It wasn't until later that I started truly looking at multiple data conditions in order to get a better picture of the equipment I was evaluating. In effect, if I look at a belt application, belt slip frequencies, and static eccentricity, I can identify that a belt or sheave is worn, belt tensioning is too tight, the sheaves are misaligned, the motor has soft foot, or any combination of the conditions. This understanding became much more valuable several years later. In 2010, we began incorporating ESA as part of our energy efficiency testing system at the repair shop using an accurate power supply, dynamometer, and an outpall 2, the next generation All-Test Pro, LLC online tester, which met the requirements for IEEE STD 112, Method B energy efficiency testing. The field service department also had multiple industrial electricians who were conversant in data collection and analysis based upon experience and training. The technology was rapidly deployed within industries from plastics and steel to critical hospital systems. Using a combination of ESA and vibration, we were quickly confirming the accurate detection of bearing defects, causes, and how soon ESA could detect bearing defects ahead of failure. As they were both used in-house and in the field, a second outpall system was purchased for service use, and a work in a range of industries, including wind power, was expanded. Additional research was also performed in the relationship between ESA and other electrical and mechanical studies, including insulation defects and degradation. I returned to consulting work in 2015 and renamed my firm MotorDoc LLC, pursuing a combination of instrument sales, field service, and reliability consulting. Several opportunities arose which included the ability to compare and contrast a variety of technologies directly, such as vibration and ESA, as well as a deeper dive into power quality impact on equipment reliability. A deeper dive into wind power systems and driven equipment analysis, which later included motion amplification. Additional work into continuous monitoring systems with electrical signature analysis led to a partnership with Framatome and the empath system with the 32-channel ECMS, empath continuous monitoring system. Following a requested study into specific rotor faults in doubly fed induction generators and related wind industry presentation, more than one-third of MotorDoc's annual work has been performed in the wind industry. Other areas of study have included AC and DC variable equipment from elevators to machine tools and transformers to power quality and additional machine learning techniques. A majority of the research has been funded by MotorDoc LLC, with practical research being applied in the field as part of service. This book expands on the original 2008 ESA and MCSA sections of Electrical Motor Diagnostics, 2nd edition, with a practical understanding of ESA and MCSA for both the researcher and with emphasis on the field application specialist. Enjoy! Howard W. Penrose, Ph.D., CMRP. President, MotorDoc LLC. A registered veteran-owned small business. Practical electrical and current signature analysis of electrical machinery and systems will be available through all bookstores, including Amazon, in both hardcover and ebook when it is released. The final announcement date will be made through the Motor Diagnostics and Motor Health newsletter and LinkedIn. You can sign up for the newsletter at the bottom of motordoc.com or empathcoms.com.